In the next three series of videos here, we're going to be taking a look at the nature of light. We'll start this video by taking a look at polarization and the ray model of light in this particular series. So here I've drawn transverse electromagnetic waves, and I'm sorry that my artwork isn't the best. Now keep in mind that when you talk about electromagnetic waves, nothing is being displaced. The vectors simply represent the values of the electric and magnetic field vectors at each of these locations. And you'll notice that the electric and magnetic field vectors are always perpendicular to each other. And again, you should convince yourself with the right-hand rule that if you take E cross B, so take your right hand, put E on the first finger, put B on the second finger, first things first, second things second, the resultant on your thumb should point to the right, which is the direction of propagation that I've drawn for these waves. Now, I've mentioned before when we were talking about producing electromagnetic waves that as a practical matter, it's very hard to detect the magnetic component of the electromagnetic wave. It can be done with specialized lab equipment, but almost all means of detecting electromagnetic waves, be that the chemical dyes in the rods and cones of your eye, the charge coupled device in the back of your camera, whatever kind of device you can think about, it's the electric field that matters. So in this example here, the electric field vector oscillates between pointing up and down. It's all confined in the y-axis. If you have that, we say that this is vertically polarized. And if the magnetic field is in sync with the electric field, then we say that it is a linear polarization. There is such a thing as circular polarization, but that's beyond the scope of this course. Now, if the oscillations of the electric field are happening in the z-axis here, going in and out of the screen, then we would say that that corresponds to horizontal polarization. So if the waving of the electric field is up and down, it's vertical. If it's the waving of the electric field is in and back and forth, it's horizontal. And again, the magnetic field goes along for the ride, but as a practical matter, we don't detect that in almost any device. Now, it is possible to make light that is polarized, but if you just say have a light bulb or something like that, like let's go and take a look at an old style incandescent light bulb with a filament here. The filament will get hot and it will start emitting light waves heading off in every direction. Now the thing is that at any particular spot on the filament, the light will be probably coming out at a different polarization. And also, for reasons beyond the scope of this course, it'll turn out that even at a particular production point, the direction of the polarization changes very rapidly from one to another. So we call that kind of light unpolarized light. So the idea here is, let's say this is the direction of propagation of our light wave. And let me give myself a little more room. This is the direction of propagation of my light wave. We usually draw it as just like some sort of higgledy-piggledy mismatch of electric field vectors oscillating in all kinds of directions perpendicular, and that's because different bits come off at different points, and the fact that it's all changing very rapidly, it basically at any given moment the direction of polarization is more or less random and it changes so quick as to hardly be noticed. So there are devices. So for instance, if you have polarized sunglasses, you could stick a sheet of polarizer in the way here. Now, the way polarizers work is kind of interesting. Most of them are some sort of a long chain polymer, like so. And I'm trying to draw these very long chain molecules that are rigged up in such a way that they have the property that the valence electrons along this whole long chain are very mobile. So this has the effect of acting like a whole series of little antennas all in parallel with each other. If you were to say go and look at a cooling rack that you cool your cookies off on, or a barbecue grill grate or something like that, that's the kind of arrangement that I'm talking about. And in fact, if the light in question were microwaves, that is exactly what you would be using for a polarizer, is some sort of contraption that looks kind of like that. But here with visible light, it's usually a piece of plastic with these special molecules that have been all aligned to point basically in one direction. They all act like little antennas. So now let's go and take a look at, say, a typical bit of the light coming in. So say this, I'm trying to show it being a little off of the horizontal axis right here. I'll draw in the horizontal axis so that we've got some context. So let's say it's tilted at some angle to the horizontal. So now what will happen is the component of the electric field that is parallel to all these zillions of little antennas, it'll start causing the electrons to slosh back and forth. And so that component of the electric field winds up getting absorbed because it's doing work on the electrons and causing the sheet of Polaroid to warm up slightly. However, the bit that's perpendicular to all the little bits of Polaroid, all the little antennas in the Polaroid, since you can't really bob the electron up and down worth a hill of beans, that vertical bit there, just shoots through undisturbed. So again, we are usually more interested in what it does in the end result rather than what it does. So we don't think about how it's absorbing. We think about the bit that's transmitted through. And the bit that's transmitted through will be perpendicular to all these little antennas. And we'll call this the polarization axis of our sheet of Polaroid. So, or the transmission axis. One or the other. So we go and take a look at what's going through. Now, a short gazillionth of a second later, the same thing will be happening with just some other random orientation of the electric field sloshing back and forth. And again, the horizontal bit here would be absorbed, the vertical bit would be passed through the way I've got this drawn. So how much light is going to pass through? Well, let's say that the initial intensity of the light coming in is I0, and you would like to know what I is equal to. This turns out to get described by what we call the 1/2 rule. There we go. So in the idea with the 1/2 rule is, let's say we are looking in on our polarizer here. And let's again say that the transmission axis is aligned vertically. The thing is that at any particular moment, the electric field will just be angled off at some arbitrary angle theta with respect to the polarization axis of the Polaroid. Okay, so let's go and take a look at that electric field vector. So this is the bit that we have initially. So this is our initial electric field vector. And then what gets passed through is just going to look like this. And it will just be the vertical component of it. So theta. So we can look at this and realize that the electric field strength that gets passed through will be the initial electric field strength times the cosine of theta. Now, if you remember from before, we showed that the intensity of the light was proportional to the electric field strength squared. So this means that the intensity of the transmitted light will be equal to the intensity of the original light times cosine squared theta. But since this is unpolarized, we're going to have to take an average of this over all possible theta. And we saw before that the average value of either sine squared or cosine squared, when you're averaging it over all possible angles, just plain turns out to be 1/2. So from that, we get that the intensity that passes through, if we have initially unpolarized light, is 1/2 of what it was before. So it'll pick up the direction of the polarization axis, and the amount of light, the intensity of the light, will be cut in half. So this is the 1/2 rule, and it's used for unpolarized, initially unpolarized light. Okay. What if the light is already polarized? Let's say it's already passed through a polarizer. What would be the case then? Well, in that case, what will come into play is what's called Malus's law. So again, it's the same logic. Here's my polarizer. We're looking at the light coming in through the polarizer. Here's my transmission axis. But now the difference is, instead of the light flipping back and forth between every possible angle, it just stays stuck at a particular angle theta. So again, it'll be the same logic. The transmitted light will pick up the direction of the direction of the new polarizer. It'll be equal to the electric field strength of the old polarizer. There's my theta times the cosine of theta. Okay, and again, since the intensity is proportional to electric field strength squared, the new intensity will be the old intensity times cosine squared theta. But here we don't need to take any averages because the direction of the polarized light never changes. So just to do an example of that, let's say we have a light source. Sure. So we have a light source here. Let's say the light coming out is initially got an intensity of 1,000 watts per square meter. It will pass through two ideal polarizers. The first one we will say is, here, let me try to draw that more edge on. There we go. The first one we will say is vertical. And then the second one will have its transmission axis tilted (60°) with respect to what we had before. Well, we know the final light, when it passes out, will be polarized, and with multiple polarizers, the rule is always the one that laughs last laughs best. So it will be tilted 30° above the horizontal like that. But let's try to figure out what this final intensity is. So the strategy here is we're going to first figure out what the intensity is after it passes through the first polarizer. And the answer from this will become the initial intensity going through the second one to get my final intensity, I2, which is what I really want. Okay, so the first step, since we said the light is just coming off of just some old-fashioned light bulb or something like that, again, it is unpolarized light, so the polarization axes are going every which way. And so when it passes through, it'll pick up the direction of the first transmission axis. So we can go ahead and say, all right, this is the case for the 1/2 rule. Unpolarized light hits polarizer, so I1 is 1/2 of I0. So it'll be 1/2 of 1,000 watts per square meter, which is 500 watts per square meter. Now to get I2, since this light is initially polarized now, this is polarized light hitting a polarizer, that one's going to need Malus's law. And what's going to count is the angle between the polarization axes, which in this case is 60°. So we can say that I2 will be equal to I1 times cosine squared 60°. That will be 500 watts per square meter times cosine squared 60, which cosine of 60 is 1/2. So cosine squared will be 1/2 squared, which is 1/4. So we are left with 125. Whoops. We are left with 125 watts per square meter. Okay, so in the next one, we will start taking a look at ray optics and explore reflection.